Say for example, if we have a register called RA and it is 4-bit in size, so I will write LSB as A0, A1, A2, and A3. And let us consider the value of this register is something like 7. So how I write 7 in binary? 0, 1, 1, 1. And then I need to write +1 to this. So if I increment the value of 1, then this 7 will become 8, and it turns out to be like this. Now, how do we design this logical diagram? How do we design the micro operation digital component for this digital module for a 4-bit incrementer? Now, how many bits we are adding? Only 2 bits we are going to add, and that is the maximum number of bits. If we are adding only 2 bits, then we use which type of adder? We use half adder. What is the symbol for the half adder? The symbol for the adder is given like this. So this is an half adder. There will be 2 inputs for this. Input number 0, input number 1, and there will be what? And 2 output, that is sum and carry. So this is half adder. And how do we represent symbolically the full adder? So we have a full adder wherein it will have 2 inputs, and the third input will be act as what? Carry in. And then there will be having 2 outputs, sum and carry. So this is the third bit. Along with the third bit, it is going to add the 2 inputs. So this is the full adder. Now, if you look at the binary incrementer, we don't require the third bit part here because the value is just incremented by 1. So therefore, to design a 4-bit binary incrementer, we may not require full adder for this. I will make use of half adder. So I will be designing the logical component for 4-bit incrementer. So I will, since it is 4-bit, then I need to have such 4 half adders: A1, A2, and then A3. Okay. And what about this? This will be fixed. Incrementing means increment the value by always 1. So we are not going to increment by 2 or increment by 3. Increment means always the original value content will be added with 1. Now this one will be hard coded. This one is what? Hard coded. Right. Now there will be this adder will form a sum and it will form a carry. So this is sum 0. Now whatever the carry it will produce, it will go where? It will act as what? It will be passed to the as input to the next half adder. Now look at this diagram. 1 plus 1. So it is 1, 0. So sum is 0. Now this carry, whatever it has generated, it will go and act as an input to the next half adder. Okay. And again, this will be producing its own sum, and the carry, whatever it has produced, it will go and act as what? The input to the next half adder, next adjacent bit addition. Again, this will produce its own sum, and then it will produce what? Its carry, and that carry will be act as an input to the next half adder. Again, it will produce its own sum, and finally we will be having what? Carry out. So this logical diagram shows a 4-bit binary incrementer. Likewise, you can do a 4-bit binary decrementer also. What is decrementer? The original value of the register must be subtracted by 1. So you can use half subtractor. Design the hardware digital component. It is RTL, register transfer language. To write the register transfer language, we need to learn micro operations, how to write the micro operations, right? So that is the major objective of this unit. Here we are going to design the complete ALU, but not in one shot. We are going step by step. We have designed 4-bit adder cum subtractor. Then we have designed a 4-bit incrementer. Likewise, for a simple arithmetic circuit, what kind of arithmetic operations you want to perform, you want to have in your processor? Say, for example, I need an addition, A plus B, and consider my system is 4-bit. So, okay, so the processor is 4-bit, and what kind of arithmetic operations I need to carry out. So I'm listing it out. So I want to perform add micro operation. Why I'm calling it as add micro operation? Remember, micro operations are those operations which are performed on the data that are stored in register. Okay. So first operation is add. Even I can have add with carry. So what is add with carry? I can represent it as two registers content is added along with the carry. So this is add with carry. I can write it as ADC in short. Even I can have what? Subtract with borrow. So this is subtract with borrow. In logically, how we write the Boolean expression for subtract with borrow? A plus B bar. And if you want to use this is subtract with borrow, subtract with borrow. And if you want to have a normal subtraction, what is normal subtraction? A minus B, right? So how do we write A minus B? A plus B bar plus 1, right? Okay. Now you want to transfer one content to another register, then we can have, say, for something like this, A. The value of register A needs to be transferred. Whether it is 0 or 1, we will see it later. Okay. And you want an incrementer. So incrementer A plus 1. You want decrementer A minus 1. Likewise, we can define, this is also transfer A. And here what we are going to transfer, A containing 1 we are going to transfer. Here, this is transfer A where A contains 0. A contains what? 0. This we call it as increment A, and this we call it as decrement A. Is that fine? Now, if you look closely, what we are going to do here, first I am designing the logic table, truth table for this, and later in the next stage, I am going to design the digital component for this. Using either multiplexer, decoder, whatever the logic fits to implement to design this ALU, we are going to use those digital components. Now, if you look at closely all these expressions, how many arithmetic operations we have defined? Now, if you look at all the 8 logical expression, what is common in this?
Sir, A.
A is common. So I will write here common variable is A. Right? Okay. Now to the ALU, when I'm designing that arithmetic unit, the A will be given directly to that hardware. A comes directly because A is common everywhere. Now, what about the B, variable B? We need either B
And B bar.
and B bar, right? So either we need the original B or the complement of B. And which was the other parameters? There is some constant also, right?
1.
We have a constant 1.
1.
And we have a constant called 0. But for common variable, we don't have A and its complement of A. If you look at this, all 8 expressions. So these are my observations now. When I decided to implement or to design 8 such arithmetic operations, and looking at the 8 such operations, I came to conclusion that variable A does not change. For variable B, sometimes I need B and sometimes I need B bar. And we need sometimes constant 1 and sometimes constant 0. Okay. The other input is what? It is changing at B. Here we require only B. Here also we require B. Here we require B bar. Here we require B bar again. Here we require what? What we require?
0.
1.
0. 0.
A. 0. We require A. A is common, right? A is common. Fine. And here also, now for this increment, now as of now, we don't require B right here, right? And we require A plus 0. And here we require A plus 1. then also I will write it here 0, but I will pass it as a carry. Carry will be added. Okay. And here I'm going to write it as both 1, 1. I will answer you why I have written this as zeros and this as ones. Now look at this carry in. For this, we don't require any carry. So I will write it 0. For this, I require a carry. And for this, again, I don't require carry. For this, again, I will require carry. For this, I don't require a carry. And here I require a carry. Now this 1 is being added with the carry, not with the input. That's why I have written input as 0. A is a common input. Carry in is 0, but I'm going to take input from here as 1. Okay. And this is transfer. This is 1 again. Now again, there is a conflict. Why we don't need anything here, right? We don't need anything here. Similarly, this transfer A, here also it is transfer A, but what we have said here, we are transferring 0. Here we are transferring 1. How do you decide that we are transferring 0 or transferring 1? That depends upon this. Here we say transfer 1. So this is 1. And this is what? Transfer 0. And how do I decide whether it is 0 transfer or 1 transfer? That depends upon this input, this control line. If it is both are 0, if it is 0, we are going to transfer 0. If this is 1, we are going to transfer 1. So that is why the reason we have written over here 1, 1 and 0, 0. Any question? Is that fine?
Yes, sir.
I will be having only 4 combinations now. How many expressions we have? 8 expressions we have. Now I have decided that I have grouped into 4. This as one combination, this as another combination, and this as another combination. I have totally grouped into 4 now. So I'm going to use 4:1 multiplexer. 4:1 multiplexer, right? So if it is 4:1 multiplexer, then how many select lines we require?
2.
How many? 2 select lines are required. How to find out the select lines? You need to keep this multiplexer in the powers of what? 2:n is to 1. So
Yes.
2:2 So 2 select lines are required. So now I'm going to write this as S1 and S0. 0, 0. Again, this is 0, 0. This is one combination. And where it is changing? With the help of carry, it is changing. Right? And this is 0, 1, 0, 1 for this. Again, where it is changing for these 2 combination, that depends upon carry, whether it is 0 or 1 for this combination of select lines. And this is 1, 0, 1, 0. Again, where it changes from 1, 0, 1, 0, how it will differentiate between this? Again, with the help of carry bit 0, 1. And lastly, we have 1, 1, 1, 1. And again, how I differentiate between these 2 select lines, 1, 1, 1, 1. It is common, but how we are going to differentiate among this? 0, 1. That depends upon the carry. Like that. We are going to make use of 4:1 multiplexer. So this is how I'm going to represent 4:1 multiplexer. Okay. Right. Now, out of this, there will be 2 select lines we require. 2 select lines. So I will mark this as 2 select lines. And I'm going to control these 2 select lines with S1 and S0. So this is S1, S0, S1, S0, S1, S0, S1, and S0. Okay. I'm not going to draw this line because there will be a lot of wires will be there in drawing. So I'm going to make use of the color code here. Now these lines, as if they are connected, S1 is connected to S1 and S0 is connected to S0. Again, the same line, S1 is connected to here, S0 is connected to here. Okay, so this is how you need to consider. And what are the 4 options we need in this 4 option? This is the first option. You need B, or you need B bar, or you need 0, or you need what? 1. Here we have B. So the blue color line is B. Here also we require B. Okay. Now, then what I need? B bar I need, right? So I will use this color for B bar. How to generate B bar? So I can generate B bar with the help of NOT gate, right? So this is B. If I connect NOT gate, this will be B bar. Now all this B bar will be connected to the second option. So this is B bar. Actually, in the textbook, they have connected with lines, but I'm using the color coding for this so that it will be easy for us. It will be easy to understand B bar. Okay, now go back to the truth table now. I have done B. I have done B bar. What else I need? I need 0 or 1. So I will write over here. Somewhere at the down, I'm going to write, and I will take a different color again for this. A green color will be act as 0. And for this 0, if I connect a NOT gate, it will produce what? 1. Okay. For one, the third input is 0. That is the green color. 0 line is connected here. 1. Purple color. So the purple color I'm going to connect here. If S1 and S0 both are 0, 0, you are selected B. If it is 0, 1, we are going to select B bar. If it is 1, 0, we are selecting 0. If it is 1, 1, we are selecting what? 1. Is there any confusion till this stage? Any doubt?
No, sir.
Okay. Now next we will, what I need to do, look at the truth table. Once we select the input, either I need to do A plus B or A plus B plus 1 I need to. So this is full adder. One of the input to the full adder is what? A common reg. Okay. And then comes what? A B. It comes with what? A B. So what I do here, one of the input to this is A, and the other inputs come from where? Okay, na? Right. Now similarly, we have another full adder. Again, for this full adder, we need A, and this full adder also requires input A, and another full adder we require input A. The another input for full adder for this first one will come out from this. From second, it will come out from here, and the third one it comes out of here, and this it comes out. Why we require 4 full adders? Because 4-bit. The reason behind drawing this 4 full adders is what? To add individual bits like this here, right? So how we have done here? A0, A1, A2, A3, and the full adders also we have drawn, right? Here, A0, B0, full adder 1, A1, B1, full adder, A2, B2, full adder. So what kind of arithmetic circuit we are going to draw here? It is 4-bit, right? So we are designing a 4-bit ALU. So therefore we need what? 4 full adders. Now this will represent what? The answer D0, that is LSB, D1, D2, and this is D3. Finally, we need to make use of this carry. The carry should be either 0 or 1. Carry should be either 0 or 1. Correct. Now, I will connect carry to here. So this carry, I will make use of a different color for this. This is carry. Now this carry will be connected to LSB, and the carry out of this will be connected to here. The carry out of from this bit will be passed to the next higher bits and next higher bit, and finally the carry will be. So this is carry in. You can call this as carry 1. You can call this as carry 2. You can call it as carry 3, and finally it will be carry out. how they have done in the textbook. They have done in the textbook this blue color line. I will draw this one. This blue color line will be drawn to blue color, and this blue color को जानना है B, okay, and this is black color B bar. So I will make use of a black color, and this you need to connect here, and this will go to B bar. This goes to B bar. This is routing the wires, okay, B bar. And then similarly for 0. So 0 is here, right? So I'm going to extend this line up to here. 0 you connect here, 0 you connect here, and then 0 you need to place over here, 0 you need to place over here. And finally, we have 1. And how 1 is produced? By connecting a NOT gate. So here we have 1. So I will extend this line to here, 1 over here, then 1 over here, 1 over here, and 1 over here. Is that fine? And similarly, they have even connected these lines from S1 and S0. Okay, so I can connect like this. This is S1 and this is S0. So S1 line I will drag over here, and S0 line I will drag over here. Now you can connect it. S0 to S0, S1 to S, like this. And this is S1. So connect to S1, and this is S0, connect to S0. Similarly for this S1, and this is S0. Okay, this is S1, and the next line is, now you take any random operations. We will take add. Okay, so for this add, what we need, how to set up now control signal, where to set up 0 0. Now look at this, set up S1 as 0, S0 as 0. Control unit, when you write, right, when something add R0 comma R1, where R0 is of size 4-bit and R1 size is also 4-bit. Once it receives fetch the instruction, it will place in the instruction register. In IR, it will be available. From IR, it will decode it. After decoding, it will perform what? An add instruction. Add instruction means what? Add is not understood by the processor, right? It understands only zeros and ones. For add, they have decoded it as what? 0 0. For add, they have decoded what? 0 0. Now the microcontroller inside the process, the control unit will generate 0 0. Now you put this as into 0 0. What is selected? What is selected now for select line 0 0? Can anyone tell me?
B.
Sir, please repeat again.
If I select 0 0, see, this is add instruction. According to our truth table, what we have done in the truth table, add A and B. Register A needs to be added with register B. Here, but I have taken the two different names. You can consider this as add register A content with register B content. If I want to add register A content with register B content, it will, after decoding, it will identify that the content of register A needs to be added with the content of register B. अभी ADD को क्या बोलेंगे? ADD we will not understand by the processor, right? So for ADD, we have decoded it for what? 0 0. We have decoded it for 0 0, right? So now what we will do? We will set here 0 0. If it is select line, S1 is 0 and S0 is 0, which line it will select? In all the 4 multiplexer, the blue color one, the black color one, or the green or the purple?
Blue one.
Blue one, right? From Now from here, what I will get? From here, I will get B. From here, I will get B. From here, I will get B. And from here also, I will get B. Is that right? Correct?
Yes, sir.
Now, this will be added with A. So A plus B we are doing. Means A naught is added with B naught. If it is 4-bit, A1 is added with B1. A2 is added with B2. A3 is added with, these are bitwise addition we are going to do. A3 is added with B3. That is what we say in the truth table. If A plus B add, if we write register A comma register B, then how the processor will think after reading the instruction from the memory and placing into the instruction register, it will decode. And how it will decode? Add, it has made it what? 0, 0 along with carry in equal to 0. Now what should be the carry in if I want to add A naught plus B naught? What it should be here?
0.
It should be 0, right? So therefore, along there is, we will tell that add A plus B means there is no carry. So carry will be considered as 0. So it will consider carry as 0. So I will write it here like this. Now, say you have written in a program like this. Add with carry A comma B. Now this is also one of the instruction. From the program memory, it will fetch that instruction and it place into IR register. And after placing into IR register, it will go into decode phase. It will decode. It should be add with carry. Now what it will do? Add with carry means what? Add with carry means, now refer now, we have hard coded now. Add with carry means select line should be 0, 0 and carry in should be 1. Carry in should be 1. So here select line S1 equal to 0, S not equal to 0 and carry in equal to 1, because we are telling it is add with carry. So automatically what it will do? It will replace this case 0 with 1. So it will be set to 1. And again it will be 0, 0. Again it will select B naught. So A naught plus B naught along with the carry. So this carry is not added with all the full adders, right? This carry in is added to only the first full adder. Now whatever the carry generated after the addition of the LSB, it will pass to the next higher bit. So therefore we have connected here. So carry in is not connected to everywhere. Carry in will go to the first LSB, first full adder, and then after addition of A naught, B naught, if the carry is generated, this is sum. If the carry is generated, it will pass to the next full adder, and this continues. You take any other instruction, random instruction we will take. Say for example, I want to perform subtract. To perform subtract, what should be the select line now? 0, 1. Now check whether subtract I have written subtract A comma B. That is, I need to perform A minus B. That is A plus B bar plus 1. To perform subtract, we have hard coded the code as what? The S1 should be what? 0 and S0 should be 1. Now set this one. S1 is 0. If it is 0, 1, what it is going to select? The black one, correct? 0, 1 means what? B bar it will select. B bar. So here at the output, we are going to get B bar. Here also we are going to get B bar. Here also we are going to get B bar, B bar. But the only difference is what? It is the bit number. B0 B bar, B1 B bar, and this, and so on. And A0 B0 bar. And what about the carry? Look into the carry. So we have told it is plus 1. So carry is also equal to 1. So for subtract, we have this option. S1 should be 0, S0 should be 1, and carry in should be equal to
0.
1.
Yes,
Look at
sir.
it. Carry in should be 1. S1 should be 0, S0 should be. If carry in is 0, then it is only subtract with borrow. A plus B bar it is.
Yes.
Got it? Now,
Yes.
if you look at this add, then it is equivalent to what? 0, 0, 0. If it is add with carry, it is equivalent to 0, 0, 1. If it is subtract, then it is 0, 1, 1. If it is subtract with borrow, it is 0, 1, 0. Are we not putting in only in terms of zeros and ones? Answer is yes. So inside the electronics digital component, this logical design arithmetic circuit, what we are designing is a simple ALU circuit. Now we will tell the programmer, write program in an assembly language, and how many instructions you have? You have only 8 instructions defined for it. If you want more instruction to be defined, then this truth table will expand them. And the complexity of your ALU will also increase at the same time. For demonstration, how this micro operations will work and how to design a logical decision, for that purpose, we have taken a very simple ALU, that is 4-bit ALU, which will have only 8 operations execution power. Only 8 features we have defined. And how this has been hard-coded with zeros and ones, I have demonstrated. So this is an example for 4-bit arithmetic unit circuit.